All right, we're going to take a little bit of detour from the normal course of looking at reactions and mechanisms and synthesis and all of that. And we're going to look at how we really verify the reactions in our lab work. Did they work? I should say. And it's kind of a way to look at molecules, to actually quote unquote see molecules without actually being able to see their structure. And one of the techniques that we use to do this is known as spectroscopy. And a spectroscopy is a technique that measures an energy change when a molecule interacts with a particular form of electromagnetic radiation, or what we call EMR. And so we expose a molecule to some certain form of EMR, and something about it changes. And we measure that change, and it gives us a piece of information about the structure of that compound. And different forms of spectroscopy will give us different forms of information. And so some of the types that we're going to be talking about over the next few chapters and even later on, we'll be focusing on infrared spectroscopy with this unit. In a couple of units, we'll talk about nuclear magnetic resonance, and then a little bit later, we'll talk about UV visible spectroscopy. Now, closely related to this, and this will occur in the second half of this unit, is we're going to talk about spectrometry. And it's related to spectroscopy, but we don't use EMR. But this is a technique that does something to a molecule that we can measure, but it doesn't utilize electromagnetic radiation. And just to highlight very quickly what EMR is, and you may have seen something like this if you've taken physics or some sort of science course that deals with physics. But this is the EMR spectrum, and we've associated with these forms of EMR in some way, shape, or form. And you can kind of see that there's different energies of these forms of EMR. So we're kind of going from high energy down to low energy here. And then kind of the inverse of that, we're going from wavelength, how big the waves are. If you remember wavelength from general chemistry, um, we're going from high wavelength to low wavelength here. And so what we're going to focus on for this unit is looking at infrared radiation. So just outside the red portion of the EMR spectrum. And we're going to look at what happens when a molecule is irradiated with infrared light and what that tells us. And we've had some experience with infrared spectroscopy in lab, but up until now, we haven't really gone in depth into it. We've just been kind of looking at two different pictures, maybe one of a reactant and a product, and then just seeing what's different. But now we'll be able to interpret an infrared spectra. So what this form of spectroscopy does is it measures the transitions between vibrational levels. And what I want you to do is think about a bond between two atoms as a spring with two masses on it. So, for example, if we take a carbon-oxygen bond here, and that, if we kind of look at it like that bond was a spring, this bond is kind of in, maybe we compress it like a spring where it kind of compresses and then goes back out. And then, the oxygen, goes in and then goes out. Think of it like a spring. But then what happens is if we expose that to infrared light, then that change gets bigger. There's a lot more compression and then decompression and so on and so forth. And really, this kind of measures a big change in the dipole moment. And what this is mostly used for, what infrared spectroscopy is used for, is to determine what functional groups are present in a molecule. Because a carbon-oxygen single bond will vibrate at a different frequency than, say, an oxygen-hydrogen bond. Or even a carbon-carbon double bond will vibrate at a different frequency than a carbon-carbon triple bond. And so by just knowing some simple values at where these things will vibrate, we'll be able to tell what functional groups are present when we read a spectra. Now, the way that these are calculated is, again, let's assume that a bond between two atoms is like a spring with two masses. And the frequency that we would expect these bonds to vibrate at is governed by something known as Hooke's law, which basically says the vibrational frequency is equal to some constant, 4.12. Don't worry about that constant. You don't even have to worry about this formula. I just want you to know kind of the pieces of it. But in this square root, we have something known as the force constant. And then we have something on the bottom term here known as reduced mass. Again, this is known as Hooke's law. So Hooke's law says that the vibrational frequency of a spring is directly proportional to the force constant, to K, and inversely proportional to the masses on the spring. Now, in terms of molecules and chemical bonds, that force constant is simply the difference between a single bond, a double bond, and a triple bond. So the force constant for a triple bond is higher than that of a double bond, and that's higher than the force constant for a single bond. And then reduced mass, while you're never going to have to calculate this, this is how reduced mass is found. It's the product of the two masses divided by the sum of them. But the key thing to remember is that the bigger this value of U, so the bigger the mass is, the slower that quote unquote spring will vibrate. And so again, the key thing that I want you to get here is that the frequency, that number is going to be higher depending on the type of bond, and it will be inversely proportional to mass. So that means the bigger things are going to vibrate slower than the smaller things. And then just to kind of round out this initial introduction, you're going to hear me use these terms stretching and bending when I describe an absorption. It's really what it is just kind of the direction the atoms are vibrating in relationship to that quote unquote that spring-like nature. So stretching is where the bond actually stretches out. So we go from short to longer. And symmetric is when on two sides they happen at the same time or in the same direction. Asymmetric stretching is where one stretches in one direction and the other stretches in the opposite. Again, I'm not going to test you on this. I just want you to kind of know when I talk about stretching, what that means. And then there's bending, where instead of the bonds stretching out, the atoms will bend in such a way either towards each other, like imagine a pair of scissors, or they'll twist around that central carbon atom, or whatever that central atom is. And so, as I said, you'll hear me describe absorptions as either a stretch, like a CH stretch, or a carbon-oxygen bend, or something like that. And that's what I'm referring to in this case. So in the next video, we're going to kind of break down how do we interpret an IR and how to make it kind of simple in terms of breaking an IR spectra down into regions.